And then if we have two chi-square distribution with degree of freedom P and Q, and if these two, suppose we have random variable x and y that follows chi-square distribution with degree of freedom P and Q respectively, and suppose they are independent of each other, then x plus y should follow chi-square distribution with degree of freedom P plus Q. If we combine 2 and 3, it means that if we add independent square of independent standard normal distribution n times, it should follow chi-square distribution with degree of freedom n. Next, suppose x follows standard normal distribution, y follows chi-square distribution with degree of freedom n. And if x and y are independent of each other, then x over root y over n follows t distribution now with degree of freedom n. And then, so number 4 and number 5 is important because we will, actually number 5 is important, and yeah, number 5 and number 2 is important. Anyway, for number 5, if x follows chi-square distribution P, degree of freedom P, and y follows chi-square distribution with degree of freedom Q, and if x and y are independent, then x over P, y over Q should follow now F distribution with P and Q. And then important thing is that about 6 and 7, T distribution converges to standard normal distribution if degree of freedom is large. And then F distribution, multiplication of P and F, Pn follows chi-square distribution with degree of freedom P. Number 8, if we square T distribution with the degree of freedom n, then it is basically F distribution with degree of freedom 1 and n. Okay. Please remember this. And then let's review briefly what we have learned 2 weeks ago about more on regression. 이게 So we learned dummy variable and a joint test of several regression coefficients. First, likelihood ratio test. By the way, I think our homework about likelihood test and word test is due today, no? Is it until next week or today? Let's see. I think no one submitted the homework. Yes, basically we have this why no one submitted this homework. Maybe there is a communication error. Okay, so let me change this one into the 31st. Okay. By next week, you have to do likelihood ratio test and word test, which we will about to review. Yes. 두 개 같다가 아니라 0이라고 하는 게 편하겠다. 뭐 이래도 사실 상관은 없는데. 네. 어디 보자. 이걸 보면 여기는 0이라고 표현을 했으니까 오케이, 그럼 그렇게 하죠. 네. 꼭 그러지 않아도 상관없는데. 오케이. I'm nice professor, so I'm willing to make it comfortable to you. 네. Okay, so homework. Do likelihood test such that beta for SMB and beta for HML is 0, jointly 0, and do wild test such that beta SMB and beta HML is same. They are same. Okay. Let's take a look at what is the likelihood ratio test and wild test. First, likelihood ratio test. Let yt equal sum of beta I xt I from 0 to n, and then gamma I zt I from 1 to k plus ut. And then our hypothesis is whether this entire block is usually so or not, basically. Okay? So we want to test whether this second set of information is usually or useful. If they are usually, it means coefficient for all zti should be 0, which means that gamma I is 0 for all I. So our hypothesis is the variable z are usually, which means null hypothesis, gamma I is 0 for all I. Therefore, alternative hypothesis is that gamma I is not 0 for I. So there should be at least one I, which is significantly different from 0. Okay. So equation 1 can be written in matrix form as like this one. So y is x beta plus z gamma plus u. Therefore, first we can run regression y equal xb plus e. We call this one as a restricted model. Restricted means we restrict gamma to be 0. Right? We put restriction on gamma, so they are restricted to 0. Therefore, we have only y equal xb plus e. Right? So it is a restricted model. And from this restricted model, we can calculate the residual sum of the square, which is RSSR. R is E hat prime E hat. Here, E hat is projection of y on the null space of the x, or y minus projection of the y on the space of the space spanned by x. Second, we run now unrestricted model. In the previous case, we restricted gamma to be 0, and now we don't impose such restriction and run the regression. Okay, run the regression 2 directly. So it is R. Then we calculate residual sum of the squares, which is RSSU, which is U prime hat and U prime. Here U prime is now regression of y on the null space of x and z. Or U hat is y minus projection of the y on the space spanned by both x and z. Okay, I have a quick question. If we compare the null space of x and then null space of both x and z, okay, then which one should be larger? Which one should be larger? Null space of x. So null space of the space spanned by x, and then null space of the space spanned by both x and z. Which one should be larger? Yes, right? Yeah. Because space spanned by both x and z is greater than space spanned by x. Therefore, null space of the small space should be larger. Right? Therefore, yes. Anyway, therefore, RSSR minus RSSU should be always actually greater than equal to 0. Anyway, RSSR minus RSSU equal E hat prime E hat minus U hat prime U hat. 두버경 학생 오늘 안 왔나? 아, 거기 있구나. 네. 안 보여서. You changed your hairstyle, so I was confused. Sorry. Yeah. And anyway, this should be greater than equal to 0 always. And then again, E hat prime E hat is y prime I minus pxy minus y prime I minus pxz. Right? Therefore, if we put those projection terms together, then it is I minus y prime, I minus px minus I plus pxz, and identity matrix cancels out. Therefore, we eventually have y prime pxz minus pxy, which should be always greater than equal to 0, as I said. I mean, intuitively, I explained it geometrically, but even arithmetically, it is so straightforward. E prime, okay, this error term, this is error term, this there, E hat is residual, regression residual, in which we consider only X, right? And U hat is regression error, in which we consider both X and Z, right? So we have more variable to calculate the U hat. Right? Therefore, U hat should be smaller always. Because if we include more and more variable, then at least we can fit curve better, right? Always. Because restricted model is a special case of unrestricted model, right? Therefore, unrestricted model should beat restricted model always. Error term should be always smaller. Anyway, so this one is still positive. Also, it is actually, I don't want to prove this, but y prime pxz minus pxy should follow chi-square distribution with degree of freedom k. Here k is what? K is number of restriction. Here k is, we have k number of z. So it is k number of variables. So which is we are arguing that those k number of variables are userless, which means that those k number of coefficients are all 0. So here k is simply number of restriction. Okay, number of restriction. And then next, for unrestricted model is of residual sum of the unrestricted model is of course y prime minus I minus pxz y, and then this one follows chi-square distribution with degree of freedom t minus n plus 1 plus k. Here n plus 1 plus k is the number of the variable in unrestricted model. And then based on the facts we reviewed just before, if this RSSR R and RSSR U and RSSU are orthogonal to each other, then if they are orthogonal, they should be orthogonal to each other actually, if we believe null hypothesis, then the ratio these two should follow F distribution. And then if we have large number of data, this one should follow chi-square distribution. Okay? And then we can prove this, but geometrically, this one and this RSSR R minus RSSR U and RSSR U should be independent of each other always, right? Why? I think I explained it. Can anyone tell me why they are orthogonal to each other? Yeah. Okay. Yeah. So they are white, right? They are triangle where one is the 90 degree, and question why they are 90 degree. So why? Yes, right. Yes, that's true. Yes, because RSSU is null space of X in. Yeah, exactly. I think that's exactly right. Yeah, that's exactly what I'm about to explain. It is null space on the X and Z, right? And null space X and Z, null space of space spanned by X and Z is too long. And yet that is smaller than null, simply null space of the X, right? And RSSR is null space of the space spanned by X. And RSSR R minus RSSR U is null space spanned by X, in which, and then that part except the part where it is spanned by both X and Z. Okay? And this is spanned by, this term is spanned by X and Z. So this is large space and this is small. Okay. 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 So, right. Okay, space spanned by both X and Z should be larger than space spanned by X, right? Therefore, space spanned by the null space of the space of the null space of the space spanned by X and Z should be smaller than null space of the space spanned by X, right? Like this one. Because this one is larger, the complement of this one is smaller than this one, right? Right? And then this RSSRU is in this part, right? And RSSR minus RSSU is somewhere in this part. Right? So they are independent, orthogonal to each other. That's basic intuition. There is a difference. Anyway, so they are orthogonal to each other, so we can use F distribution. So I think I forgot to add your comment. So basically this is X and Z and this is X, so this part should be related to the Z part. Anyway, think about what happens if RSSRU becoming, as T goes independent, and of course we know it is converted to the chi-square distribution, but anyway, but this is the, so this is the fact we wanna use. Okay, if we have large number of samples, then we can use this one. Okay, we can use this one, and we have, so we can use a chi-square distribution with degree of freedom k, and we can see whether the difference is significant or not. If they are significant, we can reject null hypothesis. If it doesn't, if we cannot reject null hypothesis. Right? Alternatively, I actually recommend you to use this one. Constructive this statistic and see whether they are significant or not. So in this case, because we have two restrictions in our homework, k should be what? What should be the number for k in our homework? In order, suppose you are doing this homework, do likelihood test of beta SMB equals beta HML equals 0. What is the number of restriction here? 2, right? This means beta SMB is 0 and beta HML is 0. So K should be 2, right? Number of restriction is 2. So K is 2. What is N plus 1 plus K? N plus 1 plus K is we use, I forgot, did you use 3-factor or 4-factor model? Okay, you use 3-factor model. So since we include constant 2, so total number of independent variable is now 4. So N plus 1 plus K is 4. K is 2, right? Which means N is simply 1. Right? So in your homework, actually, I equal 0. 0 term is a constant term. And in your model, first x is, I think, market factor. Right? And in your homework, this term is size factor and value factor. So in your homework, it is very easy. So t is simply like t is like 100 or 200 or something like that. So anyway, k is 2 n plus 1 plus k. This is 4. T is number of your observation. And then what you have to do is simply first you run the regression without value factor and growth factor. Without value factor and size factor, and run the regression, calculate errors and square and sum them. And then you calculate RSSU, which is now you include both size factor and then value factor. And then you construct error term and square it and add it. Then you have RSSR and RSSU and RSSU. So you can calculate this number. Once you calculate this number, now you can check the F-test table, okay? F-distribution table. It is available on the web, or in the R, it is integrated in the R, okay? There is a function to calculate what is the p-value for specific number of F-distribution with degree of freedom, okay? Once you know p-distribution, now then you know whether you can reject or accept null hypothesis, or reject or cannot reject null hypothesis. Okay? Any question about your homework? Yes, shouldn't be difficult. Yes. 네. 나도 그게 뭔지 잘 모르겠는데 매뉴얼 보면 나왔겠지. 네. 뻔하지. 하나는 위에, 하나는 k고 하나는 t-n 플러스 1 플러스 k겠지. 데그리 오브 프리덤이 두 개가 있겠죠. F 디스트리뷰션 보면. 그러니까 하나는 왼쪽에 거고 하나는 오른쪽 거겠지 뭐. 네. 그건 나도 뭔지를 외우고 있지 않으니까 이그젠플 보면 나와 있겠지. 또 any other question? 네. 그러니까 이걸 계산하면 F 스태티스틱 값이 나오잖아. 그러니까 그 값이 F 디스트리뷰션 상에서 어디에 있는지를 알아야지. 그렇죠? 그래가지고 그게 시그니피컨트한지 안 한지를 알아야지. 0과 시그니피컨트하게 다른지 같은지를 알아야 되는 거 아니야. 네? 우리가 노멀 디스트리뷰션으로 많이 했잖아. 그렇지? 근데 노멀 디스트리뷰션 대신에 F 디스트리뷰션 사용하는 것만 다른 거지. 그렇죠? 아무튼 그 설명서를 보고 디그리 오브 프리덤이 두 개를 입력해야 되는데 두 개를 어느 쪽에 입력해야 되는지 헷갈린다. 그러면 카이스퀘어 디스트리뷰 해보면 디그리 오브 프리덤이 하나밖에 없잖아. 이걸로 해본 다음에 위에 거랑 비교해서 비슷한 값이 나오는 걸로 한쪽을 넣으면 되겠지. 그렇죠? 여러분은 샘플 사이즈가 충분하니까, 그렇죠? F로 계산하나 카이스퀘어로 계산하나 비슷하게 나올 거예요. 그렇죠? 다르게 나온다 그러면 디그리 오브 프리덤을 서로 반대로 입력한 거지. 물론 근데 매뉴얼 보면 다 나와 있을 겁니다. Any other question? Okay. And actually, yeah, you can run regression and calculate residual sum of the squares, and then you can do this way, and this is robust way and educational way. But in R, there is a simple one-line function that calculates F distribution too. That does this joint likelihood ratio test too. There is one-line command for likelihood ratio test. If we want to use that, that is fine, but still you should be able to do it this way. And next, let's go to the world test. Now, world test is let yt equal now, I equal 0 to n. Again, in your homework, n should be 4. 3 factor plus constant, and beta I, xti plus ut. And t is from 1 to t, and big T is the number of observations. And consider null hypothesis is that a specific linear combination of beta, ci beta I equals 0 to n is b. Okay. And next one is alternative hypothesis, of course, is not equal to 0. Then how we use this structure to test if two coefficients are equal to each other. Actually, this is exactly homework, right? How can you use this structure to test if two coefficients are equal to each other? How we can do that? In this case, it is easy, right? we can say 0 in your homework is 0, 0, 1, minus 1. C should be 0, 0, 1, minus 1, and B should be 0, right? So in your homework, okay, 0, 0, 1, minus 1, and then beta is a constant term, beta 0, and beta for market factor, and beta for size, and beta for HML value, and this should be 0, right? This is your null hypothesis. Then this and this are the same. So this is your null hypothesis. Okay, H null should be look like this in your homework. How can you use it to test the two coefficients are proportional to each other? Okay, this one is easy too. How can you use to test if this is slightly more difficult? Okay. Anyway, we want to derive the distribution of this one. So we want to derive the distribution of this one under the null hypothesis. Okay. If null hypothesis is right, if this is right, expectation of I from 0 to n ci beta I hat is some I from 0 to n ci e beta I hat, and because of the unbiased, this linear regression is unbiased. Okay, it is unbiased estimator. Expectation of beta I should be same to what beta I. So if null hypothesis, so up to this part, okay, from here to here, it is not really our hypothesis at all. This part is our hypothesis. Okay, this part is just automatic, and once we have this part, and if we impose hypothesis, that should be equal to P. Okay, based on our hypothesis. And how about variance of this restriction? Then variance is variance of I equal 0 to n ci beta I hat is ij cij covariance beta I beta j. So actually it is better to see matrix form. In matrix form, H null is a C prime beta is B. So again, C prime is 0, 0, 1, minus 1, and beta is beta 0, market factor beta for SML, beta for HML, and B is 0. And alternative hypothesis is not 0. So expectation of C prime beta hat should be equal to B, okay, if our null hypothesis is right. And then variance covariance matrix of Ci beta hat is C prime D beta hat C, which is C. We know what is the variance covariance matrix of beta hat, which is sigma square x prime x inverse. So which is C prime sigma square x prime x inverse C, right? So we have this part. Therefore, okay, under the null hypothesis, C prime beta hat minus B divided by S over C prime x inverse C should follow T distribution. It is not normal distribution because it is S, not sigma. Okay. If we know sigma, right, and if instead of sigma, if we have sigma instead of S, if we have sigma, then it is simply this is simply ratio of this expectation of a variance term, right? Then based on okay, then based on this term, okay, it should follow normal distribution. However, instead of this sigma, which we don't know, we have to use S, right? S. Therefore, it now becomes T distribution. S is the, yeah, N is something we know. N is like T minus 1 plus N plus K over 1 minus, right? You don't remember this one? In OLS regression, right, we have exactly the same problem. Let's go to our regression again. I think this is important. Multiple regression. in our multiple regression, multiple regression, okay, statistical property, and x looks like this, okay. Beta hat is a beta expectation of beta is x prime x inverse x prime y, and expectation of beta hat, as you know, it is beta, and variance covariance of beta is sigma x prime x inverse, and then okay, but the problem is as an estimate of sigma, we don't know sigma, so we use, instead of sigma, we use this one, okay. So we construct a t value, right? As you remember, when we test whether a specific variable, specific coefficient is the same to 0 or not, we construct basically t distribution, right? Where t distribution is basically this one minus this one, right? So here S is simply this one. And then of course, in this case, we have to use sigma s square. If we know this sigma square, then we know sigma. So there, if we put sigma instead of s, right? And then actually it is different from, it is not this one. Yes. Yeah, anyway, it is slightly different, but since we don't know sigma, right? Sigma is something we don't know, so we have to estimate it. So because this s square term follows the chi-square distribution, therefore, okay, therefore in our, because of this one, if x follows normal distribution and y follows, right, chi-square distribution, then this follows t distribution. Therefore, okay, this, okay, this one follows, this one divided by sigma square follows standard normal distribution. But if we cancel out that one with S, that follows chi-square distribution. So it is basically ratio of the standard normal distribution and chi-square distribution. So this follows t distribution. Anyway, if you have more question, you can go to our previous slide about regression. I think this is somewhere here. I cannot find it now. This is, I think I explained it, but anyway, I cannot find it right now, but I think I explained it. So anyway, this follows t distribution, so you can use it. Or alternatively, since square of the t distribution is f distribution, so instead you can use this f distribution, which is c prime beta hat minus b prime s square c prime x inverse c prime beta hat minus b. This should follow f distribution. So in your homework, it is very easy, right? In your homework, it is up to you whether you can use this one and this one. So you can simply run regression, right? You can simply run regression and you can calculate the beta, and c is given, okay? Run regression and you can calculate beta hat, and c is given, like 0, 0, 1, minus 1, and b is here 0, right? And then c is again same, and x prime x inverse is easy to calculate, so you can calculate this part. And about this s part, s is the standard error, right, of your model. So once you have an error term, simply you can calculate the standard deviation of the error term basically. If you want to be more if you calculate standard deviation of error term in R, they don't take into account this part actually, but it does not make much difference. Anyway, once you have this one, you can calculate this one, and you can do the sigma, and then you take a root, and you can calculate this one, and then you will have a specific value, and then you can compare that value with the, using that value, you can calculate p value in the t distribution, right? Then you are done. Of course, if we have large number of observation, then this t distribution should converge to normal distribution here. In this case, f distribution should converge to chi-square distribution. So anyway, you can use either z value or here chi-square value as you wish, if you have a large number. But in your homework, I recommend you to use this either f distribution or t distribution instead of normal distribution or chi-square distribution. Any questions? This shouldn't be that difficult, right? Any questions? No. Now more general word test. Now in the previous we have more general word test, and suppose C is now not factor, C is matrix. So suppose C is K by n plus 1 matrix and B is K by 1 matrix. Right? Now in the previous case we have only one restriction, right? One restriction in our homework, one restriction such that this one and this one are same. But sometimes we want to impose more than one restriction. So in this case, we have k number of restrictions. So consider C prime beta equals B. So alternative hypothesis then of course C prime beta is not same to B. So note that the first example can be written in this form where C is of course 0, I, K. So if we use this matrix notation, then expectation of C beta hat is because, of course, since beta hat, expectation of beta hat is beta, we have a C prime beta, which should be equal to B. Now variance, covariance matrix of C prime beta hat is then C prime D beta hat and C, which is C prime sigma square X prime X inverse C, which is sigma square C prime X inverse C. All right. Now we can construct now F distribution such that F distribution is now we have to divide with, it is almost similar to previous case, but now we have to divide with degree of freedom, which is K. K is again number of restrictions. So 1 over K multiplied by C prime beta hat minus B and S square C prime X inverse C inverse of C prime beta hat minus B should follow F distribution now with degree of freedom K and T minus N plus 1. And then of course if we have a large number of T, if we have enough sample, then you can simply use chi-square distribution where degree of freedom is simply number of K. Okay, I think this is enough. Now next, let's go to the omitted variable regression. Now suppose we have a model which is x equal x beta plus z gamma plus u. However, suppose econometrician like us estimates the model as y equal xb plus epsilon. He or she does not include the z variable. Then our question is what's going to happen to b? Okay, I mean what it does say is that this is true model. Okay, this is true model, and we know maybe in the true model both x and z is important. But because of our maybe information problem, we may not have information about z, right? So in that case, we may have to run regression only with x, or maybe it is a mistake of the econometrician. So anyway, originally this is what we have to run, but this is what we learned. Okay, what we will run in regression. Then our question is what would happen to our estimate if we omit some important variables. Okay. Of course, b hat is x prime x inverse x prime y. Okay, this is our estimate. But the true y is x beta plus z gamma plus u. So if we plug this true model to z, then our model is, our estimate beta hat is x prime x inverse x prime x beta plus z gamma plus u. Okay? Now we can expand this one. Then x prime x inverse x prime x beta plus x prime x inverse x prime z comma plus x prime x inverse x prime u. Okay, and then about this first term, x prime x inverse and x prime x cancel each other. So we eventually have beta hat b hat equal to beta plus x prime x inverse x prime z comma plus x prime x inverse x prime u. Okay. Thus, even if in our regression, okay, we usually assume this error term. Our hidden assumption is that error term is orthogonal or independent of x and z. And even if we accept that hypothesis, that assumption, still our estimate of beta is now, expectation of b hat is now different from beta. Right? So if we omit important variable, then our OLS estimator is not unbiased anymore. Okay, our OLS estimator is now biased estimator of the true beta. Of course, even if we omit important variables, still it is possible that we can get biased estimator if either x prime z is 0 or gamma is 0. Okay. First, let's take a look at this gamma is 0. Gamma is 0 means, okay, if gamma is 0 means that basically what we run is exactly the same to the true model, right? Because gamma equals 0 means that z is anyway unimportant variable, right? So intuitively, since we did not include unimportant variable, it does not matter whether we run this model or this model. Okay, so this is intuitive. Second one, okay, second one is more subtle. Okay, if x and z, okay, here this one and this one is okay, independent of each other, they are orthogonal to each other, then it is fine. Okay, even if we exclude this z variable, still we can get unbiased estimator. Okay. Why? Right? Because this term becomes 0 under the, okay, this term becomes 0 if x and z, okay, actually expectation of this one is 0 because x and z are orthogonal to each other. More intuitively speaking, right? Basically, this one is our true model, but if we run only this model, basically we are regressing y on the space spanned by x, right? But problem is that y includes not only u. We know that error term is always, we already know that error term u is orthogonal to x, right? But there is no guarantee. We cannot guarantee that z is orthogonal to x. But if z is orthogonal to x, if we regress y on the space spanned by x, then not only u disappear, then the z part, another important part, is also does not matter when we project y on x. So we can still get the correct estimate for beta, right? So the z part, the z gamma part is something, some information in y that is not explained by x, right? But if happen to be if that unexplained part is independent of the x, then simply projecting y on the x space, that part simply go away. So we can get the true, okay, we can get the unbiased estimator for beta. Okay, that's the intuition. And then about this term is called the bias term. What do these two special cases correspond to? I already explained the education. I think we can skip this part. Now asymptotic large sample properties. Now again, let's consider the model y equal x beta plus epsilon. And then of course whereas estimator of the beta is beta hat equals x prime x inverse x prime y. And then if we put our true model y equal x plus beta plus epsilon into y, then we have x prime x inverse x prime and x beta plus epsilon. And then therefore we have beta hat equal to beta plus x prime x inverse x prime y. And now suppose epsilon follows a normal distribution in which mi is 0, and then variance covariance term is sigma square I. Then beta is a linear combination of normal random variable and is thus itself is normal, right? Then therefore, or i.e. what we can say is beta hat is also normal. It should follow also normal distribution too. Again, because beta hat is beta plus x prime x inverse x prime y epsilon, but beta is simply constant. And second term x prime x inverse x prime epsilon is linear combination of random normal random variables. So that should follow normal distribution. Therefore, beta hat follows normal distribution with mean beta and variance sigma square x prime x inverse. And of course, if we in equation 4 we are assuming the epsilon follows normal distribution. But if we don't want to assume normal distribution, actually we cannot say, if epsilon does not follow normal distribution, now we cannot say beta hat follows normal distribution anymore. We can simply say that beta hat, the mean of beta hat is beta, and variance covariance of the beta hat is sigma square x prime x inverse. But we cannot say they follow normal distribution anymore. Then we have a problem, right? In our previous distribution theory, we basically assume beta hat follows the normal distribution. So we constructed like a t statistic, we constructed the f statistic and chi statistic and those things, right? But if this not follow normal distribution, you cannot say this anymore. Then we have a problem. But good news is that if we have large number of data, actually this approximately follows the normal distribution. So the good news is that even though we cannot assume that epsilon follows this normal distribution, if we have large number of data, still then we can use those, right? We can do those tests still. It is possible to use those those theories we learned. And I'm going to explain why. However, if we focus on the fact that t is large, if we focus on the fact, it's supposed, so it means that if t, our number of data is large, we can make much more headway by using asymptotic distribution as an approximation. Returning to the equation 3, equation 3, beta hat equal to beta plus x prime x inverse x prime epsilon. And then you can divide x prime x with t and multiply. Actually, we can put t inside of the inverse and outside. Then those two t's cancels each other out. So basically, we have beta hat equal to beta plus x prime x over t inverse and x prime epsilon over t. And by the law of large numbers, if we believe by the law of large numbers, then x prime epsilon over t should converge to 0, right? As t becomes infinity because each epsilon is 0, right? And if we assume that x prime x divided t does not explode, it converges to some constant matrix W, then what we have is that beta hat converges to beta plus W inverse and 0, which is beta, right? So if we have, which means that if we have large number of data, what we know is that beta hat will eventually converge to beta. Yeah. 그러니까 이거 말하는 거가 이거? 아니지, 로우 오브 라지 넘버스는 전혀 다른 이야기지. 그러니까 이거에 대한 질문이에요. 이거에 대한 질문이에요. 그렇지, t가 무한대로 가는 건 똑같은데 잠깐 이거하고 이거 다른 이야기인데 I think law of large numbers is very important. Okay. 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 Let's take a look at easy version of law of large numbers. Okay. I think there should be. Let's take a look at Wikipedia, Investopedia. I don't like it. Wikipedia. And law of large numbers is very important. Okay. Okay. In probability theory, the law of large numbers is a theorem that describes the result of performing the same experiment a large number of times. According to the law, the average of the result obtained from a large number of trials should be close to the expected value. So, okay, law of large is important because average becomes expected value. Okay? As I think I explained this in the very first class, right? I remember I asked you what is the difference between average and expectation, and not many of you could answer that. I remember. But anyway, so average and expectation is very different one. Okay, expected value is property of the population. Okay, average is property of the sample. But good news is that average converges to expectation because of the law of large numbers. Okay. And that's the property. So we can go to this one. Okay, so this is not exactly if. Okay, this is not exactly average. It is more like a weighted average. Okay, but x prime you can. Okay. Okay, you can regard this is x, so it is more looks complicated. But instead of x, suppose it is a vector composed with only one, right? One. Then one vector prime epsilon is the sum of the epsilon, right? And sum of the epsilon divided by number of epsilon. Okay, so it is exactly average of the epsilon. Right? But in this case, of course, it is not just one, and we have other x's, so it is not exactly average. Okay, not exactly average, but linear combination of epsilon. But still, it doesn't change much. Okay, it is like similar to weighted average, but this one, okay, this something similar to average should converge to 0. Okay, why 0? Because 0 is expectation of the each epsilon. Right? Okay. Yes, over there, right? Over there, we assume that mean of epsilon is 0, right? So this one is since expected value of epsilon is 0, and this is something like average of the epsilon, so this one should converge to 0, and this is exactly law of large numbers. And this is actually slightly different from law of large numbers, but let me explain this one later. And then let's take a look at law of large numbers more. Okay. So history. Okay. What is this? Diffusion is an EM flow. Chemistry. I don't know. Okay. Okay. Forms. The form is that right. So instead of x in our equation, it is epsilon. So this is just average, right? This one x and pi is average of the x with the sample size is small n. Okay, and then law of large numbers. Strong form of law of large numbers argues that this average converts to mu. Mu is the where is this? Mu is the expected value of each x. For n equals large. where x1, x2 are infinite sequence of independent and identically distributed integrable random variable with expected result. And then weak law of large number states that sample average converges the probability toward the expected value. So this is weak form because it means that average converges to expected value with probability 1. Okay, not absolutely with probability 1. Okay? There are slight difference between the two, actually. Yeah. Weak law and this, weak law and strong law is this one state convert almost surely. Okay, almost surely converts 1. So it is basically difference between whether limit is outside or inside of parentheses. Yeah, uniform law of large numbers, Borel's law of large numbers, proof. I think this is interesting. Okay. Okay, so this part is because of a law of large numbers, and this part is more like an assumption. Okay, assumption. So again, I mean, intuitively, this is the kind of average. In some sense, it is average, right? Because x prime x is it is average of some sort of x square. Okay, x expect average of some of the x squares. Right? But if we assume that those x don't explode as a sample size change, we can say that okay, those square terms of the x should remain stable. Okay, if they remain stable, x prime x divided t should converge to some stable matrix, right? I mean, it is more like assumption again, but x prime x over t is some sort of average of x squares. If that average exists, we can say this. And law of large numbers, if we accept this law of large numbers, and if we accept this reasonable assumption, then what we can say is that, okay, beta hat will converge to beta if we have a large number of samples. Okay. More formally, this is a law of large numbers thing, but anyway, P-lim is, we can say, the probability limit. Probability limit of the beta hat is beta if and only if beta hat equals to beta as a t of large numbers. Probability limit means that beta hat equals beta with probability 1. Okay? There is a possibility that beta hat is different from beta, but that possibility becomes 0 if we have large number of samples. More specifically, this means that probability limit of the p beta hat equals beta if and only if we have a large number of t, then the probability that beta hat and beta is within the distance epsilon is 1 for all epsilon. For whatever epsilon we take, whatever small epsilon we take, if we have large numbers, then beta hat, distance between beta hat and beta should be closer than the epsilon. If and only if. If and only if. 예. 오타 아니에요. 네. So if P-lim beta hat is beta, then we say that beta hat, okay, is consistent estimator of the beta, right? This is a very important property. Of estimator is consistent estimator of true parameter, which means that if we have a large, so it is a matter of the size of the data. Once we have a consistency problem, the remaining task is just to collect data. If we have a large number of data, then the estimator will converge to true parameter if they are consistent. So it is a very important property. So I think, okay, let me finish up to this part and take a rest. And on easy property or convenience property of a probability limit is a probability limit of the function g of the sigma theta hat. Okay, here theta hat is some estimate of a theta. Then it is the same to g of the function of the probability limit of the theta. In other words, probability limit of the function of an estimate is equal to function of the probability limit of that estimate. Of course, if p-lim probably means theta hat exists. And we need this small technical condition on G, of course, but that is satisfied in our example. Now, returning to equation 3. Equation 3 is this one, okay? Beta hat equals beta plus x prime x inverse x prime epsilon, and we divide and multiply by t, like this way. If we, from the equation 3, beta hat minus beta equals x prime x over t inverse x prime epsilon over t, okay? And next, okay, next let's multiply root t each side. Then we have root t beta hat minus beta equals x prime x over t inverse x prime epsilon over root t, right? And then, okay, basically this is similar to calculating variance covariance matrix, right? It is not exactly variance covariance matrix, but it is similar to variance covariance matrix. So probable limit of the t, okay, remember this t over here, we multiply t, and the beta hat minus beta hat minus beta square becomes, okay, so basically it's multiplication of this one 2 times. So p-lim of the, okay, this one multiplied by, okay, transpose of this one. So p-lim of the x prime x over t inverse x prime epsilon over root t, and then because it is transpose, epsilon prime x over root t and then x prime x over t inverse, right? And then of course we can simplify this one. So it is p-lim of the x prime x over t inverse x prime epsilon prime x over t and x prime x over t inverse, okay? And then now we can apply the convenience property of the p-lim. We can apply this property, okay? We can so put p-lim inside of each part. So it is a p-lim of this part and p-lim of this part and p-lim of this part. Almost. 예. 그러니까 약간 레귤레러티 컨디션이라는 게 필요한데 약간 뭐 연속이고 미분 가능하고 뭐 약간 그런 프로퍼티가 있는데 어쨌든 예. 대부분의 함수라고 우리가 아는 그냥 보통 함수, 이상한 함수 아닌 거라고 생각하면 됩니다. 그럼 만족합니다. And then because of the large numbers, actually this second part, okay, this second part becomes p-lim of the this second part is p-lim of x prime sigma square I x over t. Okay. Now we can put this sigma square part in front of this one, and then move this one again, and actually this one and this one cancels out. So we have a very important, interesting property that, okay, t multiplied by t multiplied by beta hat minus beta 뭐 이렇게 쓰지 뭐 어차피 똑같은 거니까 t 곱하기 이렇게 되잖아요, 그렇죠? We have something like this because t is inside, okay. Here t is inside of inverse matrix, so inverse of the t, 1 over t is t, so I simply plug this outside. So if we cancel this side, then it is like it is sigma square x prime x inverse, so it is like a variance covariance matrix, right? So again, this is very important property. Again, right? Okay. Now beta hat converges to beta, and this part converges to beta. So in our previous examples, in our up to now, we assume that beta is normal distribution, and since beta follows normal distribution, so we can do t-test, f-test, or chi-square test, those things, right? But now, actually we don't need that assumption anymore now, because anyway, beta hat will converge beta with large number, and this one converges this one with large number. Right? So we don't need that kind of distribution or assumption anymore, actually, if we have large numbers. So this is very important properties. Anyway, by a central limit theorem, this is called the central limit theorem. central limit theorem 내가 설명했나? 배웠나? Anyway, by the central limit theorem, okay, root t beta hat minus beta, okay, because of these two properties, this one, root t beta hat minus beta converges now normal distribution with mean 0, okay, mean 0 and v. V is simply sigma square and proper limit of the x prime x inverse over t, right? And of course, it is a matter of, actually, it is more rigorous notation. But if we are not so rigorous about the notation, actually, we can cancel this root t out. If we cancel this root t out, this one goes away, right? Then it is, and then we can move beta one over here. Then it is like, looks like this, okay? 어디 갔지? Okay. 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 We have this distribution because we assume that. Okay. Okay. If we assume normal distribution, then we know this hold, right? Okay. But now, even though we assume now we don't have this one anymore, okay, we don't assume epsilon follows normal distribution anymore, but now we have something very similar to this one, okay, which is basically this is fine. Right? So basically, this one and this one is almost the same, right? It is a consistent property, but if we delete this one, it is easy to delete this one, right? If we divide each side of this one with root t, okay, root t, then this is 0. And root t, it is a variance, so it is actually divided by t, right? So this cancels out, right? And then once we remove root t, then, once we remove root t, then we move beta over here, then basically this one and this one becomes exactly the same, right? So the point is that, okay, now the point is that even though we don't assume epsilon, even though we are not sure about this epsilon normality of the epsilon, if we have large samples, we can approximately, asymptotically, more accurately, asymptotically say that this beta also follows normal distribution asymptotically. Okay? So because this and this almost same, we can use all the previous F test or T test or chi-square test, those things, we can still use those things. So bottom line is that thus there are two ways we can talk about the distribution of beta hat. So we are eventually interested in distribution of beta hat because we have to know the distribution of beta hat, otherwise we cannot do any test about beta hat, right? So in order to talk about distribution of the beta hat, first, conveniently we can assume this one. Conveniently we can assume this one. If we assume this one, basically we are assuming this one. Okay. So the first option is simply we assume beta hat follows normal distribution. That's fine. If we hate that assumption, we can rely on asymptotically. Okay. If we hate this assumption, then if we have enough number of samples, still we have something very similar to this one. 질문 있나요? No question. So let's take 15-minute break.